We're Corey Boone and Caitlin Williams in Lab Section G, and this is Lab 10 Laser.
We have light from a Boone laser source, which is 45 degrees linearly polarized, which images the system onto a beam splitter, which splits the light to a fast detector and to a Fabry-Perot scanning detector, scanning frequency of 10 gigahertz.
With the fast detector, we measured a beat frequency of 562 megahertz, which gave us a laser cavity length of 26.69 centimeters, which is very close to the given value of 26.5. With the ruler, we measured the laser enclosure, which was 33 centimeters, giving a beat frequency of 454 megahertz, which is less than our calculated value from the fast detector, which indicates that the laser enclosure is longer than the cavity. With the Fabry-Perot, we measured on the oscilloscope a mode time spacing of 7 milliseconds, and then the repetition between the laser pulse was 127 milliseconds, which we used and divided the two, and multiplied it by the scan rate of the Fabry-Perot to get a beat frequency of 551.18 milliseconds.
To align the teeny laser, the position and tilt of this mirror were adjusted until lasing was observed. Then this attenuator was placed in the system, and the position and tilt of the mirror were continuing to be adjusted to observe different lasing modes on this piece of paper. This tube is slanted at an angle so that the incident angle of the light is Brewster's angle. Assuming the refractive index of the tube is 1.5, this Brewster's angle is 56.31 degrees. The output of the laser is horizontally polarized. We continued adjusting the position and tilt of the mirrors to find these two different lasing modes. We then continued adjusting the mirror to find the highest lasing mode we could, which was TEM34Q, which had 2 columns and 3 rows.
With light incident from a laser source on this beam profiler, we adjusted its position on the z-axis, and for every z value that we adjusted it to, we took the beam diameter for each x and y value, and put it into an Excel program. With those beam diameters, we calculated their respective beam radii, and plotted it against the position on the optical axis. With that, we graphed it and took the slope, which gave us the tangent of the half angle. Using that, we calculated the divergence angle, which gave us the 2 numerical apertures. And then using this formula over here, we were able to calculate the 2 beam widths.
Using this equation and assuming that both radii of the mirrors are infinity, the resonant frequency of the laser is found to be CQ over 2L, which is independent of the indices M and N. Letting the radius of the first mirror equal the length of the cavity, 50 centimeters, the refractive index of the cavity equal 1, and the radius of the second mirror equal infinity, the difference in resonance frequencies between modes 10Q and 00Q was found to be 150 megahertz. The difference in resonance frequencies between the modes 30Q and 00Q was found to be 450 megahertz, and the difference in resonance frequencies between the modes 11Q and 00Q was found to be 300 megahertz. Similarly to the fringes of equal inclination, the parallel mirrors in the Fabry-Perot are moved by the piezoelectric, causing 2-point interference and flickers.
This has been Caitlin and Corey with your weekly installment of Video Lab Reports.